what really does an embedded system designer do? So in the real world, when you are building a product, what are the kind of problems that an embedded system designer is called upon to solve? So maybe we will start by looking at that, and that hopefully will lead us on to look at specific subsystems that might be interesting to learn, and also maybe will lead us on in the direction of what questions are important to address when we look at these subsystems. So let us start by looking at what an embedded system designer does, and I think the easiest way to get there is to take an example product. Right, you are probably familiar with the concept of a product teardown, where somebody sort of opens the product completely, looks at what ICs go into the product, who is supplying what the capabilities are, so on and so forth. So we will try to do that, but with a block diagramish approach, and we'll take something that maybe most of you have used. Right, so we will look at a Bluetooth headset. All of you would be familiar with what a Bluetooth headset is. It is a wireless device that you use to stream music from your phone, maybe make and answer phone calls, activate the voice assistant, etc. And depending on how much you are willing to shell out by way of buying the product, there might be added features with respect to noise cancellation, spatial audio, maybe communication between people that have the same headset, etc. Right. So let us look at a Bluetooth headset. Let us try to see, okay, what might go into that Bluetooth headset, and from there work our way towards understanding what all subsystems are part of that, are part of a product like that, and which of those subsystems are pure analog, which of those subsystems are pure digital, which of those subsystems are mixed signal, and we will work our way from there. Okay, so let us start with the product we are going to look at is the Bluetooth headset. So like I said, what do you use the Bluetooth headset for? You use it to stream music from a phone. That is the use case. So let us start with that use case. So let us say I have a phone, I want to listen to music, and this right here is what I will call my device, right. So what has to happen now? My phone is, let us say I open Spotify on my phone, I start streaming music. What the phone now will do is, because there is a wireless connection between the phone and my device, it is going to say, okay, I am going to transmit through some protocol, again through Bluetooth in this case, because the headset is a Bluetooth headset, transmit over the Bluetooth protocol packets that comprise the music. So there is information that is flowing in the air like this. So what you need to do first is you have to receive the music packets, right. That is step 1. And now let us say, oh, okay, I received the music packets, can I just play them? Is that all I have to do, or is that something else I need to do before that? And one way to see what else you might want to do between this and, let us say, okay, I have to play the music. So at some point I have to have a driver for the headphone. So I eventually have to drive the headphone. So is it only a case of receive the music packets and then just play it through the driver, or does something else have to happen in between? In that context, it is again is interesting to think about. Again, we are embracing the role of an embedded system engineer. So it is interesting to think about, okay, how much information are we sending here, right? So let us say, for example, let me work my way to the next page. So let us say, just going back to the same example, Now I am interested in audio streaming. Now audio streaming comes in different forms, right. So if there is something called HD audio, high definition audio means that you can listen to anything that you are without any error reproducing faithfully the original music recording. So the audio is reproduced from 20 hertz to 20 kilohertz, which is what humans can hear, and with sufficient bit fidelity or sufficient dynamic range. So you would have to at least do 16 bits at 48 kilohertz sample rate. This is the minimum you have to do. Now depending on how pristine you want your audio to be, this can go up to 24 bit at 96 kilohertz or 24 bit at even 192 kilohertz. This is I would say very good audio. So now if you use this to calculate the data rate, and this you would want to listen to stereo music. Stereo music means you have two channels, left and right, so you need to send twice the amount of data. So this data rate will now be 16 bit into 48 kilohertz into 2. This is I think 1.536 megabits per second, and this would be 24 bit into 96 kilohertz into 2, which will be about 3 times this number. So 4.608 megabits per second. Now this is the raw amount of information that has to go across the channel. So if I was just transmitting music as is, the amount of information that has to go over this channel is defined by this calculation, right. So now we said it's a Bluetooth headset. Bluetooth, depending on the type of the variation of the protocol you use, you can get 1, 2 or 3 megabits per second, but that is the raw data rate that is possible. The actual achievable data rate, is usually much less, and there is also the trade-off between the data rate you want to support and the amount of range you will get. So you could be walking, jogging, your phone could be in your back pocket, could be wearing jeans. So it can happen that there is a fair bit of interference between your phone and the headset, and it is important that music not break in a scenario like that. Right. So it is important to reduce the amount of information that is going over the channel, so you get as much range as possible. Channel bandwidth is strongly correlated with the amount of range you can get. Higher the channel bandwidth utilization, lower the range you are going to get. So what people do is, again it's a very long story to say something small. What people do is say that, okay, I am not going to, let us say I want 1.536 megabits of raw audio data. So I want 16 bits at 48 kilohertz stereo. I am not going to transmit it as is. I am going to compress that information with a codec before I transmit, and that coding compression gain could be 4, 8, 16 depending on the type of codec you use. So that allows you to bring down the data rate to a point that it is possible to get range by keeping the channel bandwidth low. So now what you are getting here is, hence this is coded data, which means that one of the first things you need to do is decode the music packets. In other words, you get coded data, you have to convert it to what is called raw format or PCM format. PCM format would now be 16 bits or 24 bits, how many ever bits you decide to stuff your data with, and at the sample rate that you are sending it. So it could be 16 bits at 48 kilohertz, 24 bits at 96 kilohertz, or if you are an audio file, can even be 24 bits at 192 kilohertz. Once you do this, then you might want to do some conditioning on the audio. So let us say use cases you might be familiar with, noise suppression. So if you have an earbud, for example, let us say an AirPod or an equivalent of an AirPod, it allows you to dim the amount of external noise, and it is doing that through some sort of audio conditioning. Or you can say, no, I want something even more advanced, I want spatial audio, so that I can get that sense of immersive audio, a concert like experience where I know where the audio is coming from. The spatial audio effect is created through, again, audio conditioning. These are complex systems that I am simplifying to a extremely high degree, but I think it's valuable to do that to get a sense of, oh, okay, this is how you put this system together, right. So now there is a audio conditioning block. So this usually is a DSP of some sort. After the DSP, there is a driver, and I am using a generic term driver. It means that there is this is still digital data. After this, there is a digital to analog converter, which then feeds the analog driver, which will drive the headphone. So here I probably have headphone left and headphone right, which are the actual earpiece. So could be 16 ohms, 32 ohms load, and that is what the driver will drive. So now this is in many ways maybe the simplest block diagram you can think of for a music streaming use case, where you say that, okay, I am streaming music, what might be the minimum set of blocks I have to go past. So the minimum set of blocks again would be the receiver, which is receiving the music packets from the air. So there would be an antenna, an RF front end, and then an analog baseband and a digital baseband, followed by a link layer, and we will come to this in a minute. But that is sort of what the receiver will have, at which point the transmitted packets are available at the received side. Now these packets are coded packets, which means music has been compressed to reduce the channel bandwidth or reduce the utilization of the channel bandwidth. So that has to be decoded. So there is a decoder followed by some audio conditioning, which is maybe done by a digital signal processor or a DSP, followed by the driver circuits. So and we are talking very simple use cases, right. We could do something very similar for phone calls also. Maybe we will do that and then look at the subsystem. So let us work our way down a little bit here. I am just going to minimize this a bit, and then we will talk about the phone call use case. So again, same thing, I have a phone, I am getting a phone call, pardon my drawings. So over the air, I am going to both receive voice from whoever is speaking to me, and also transmit my voice to the person I am speaking to. So if you now look at this block diagram, this is my device. What I will have is, I will have a receive voice packets, where I am essentially receiving what the other person is telling me. I will also be transmitting voice packets, which is information from me, which is my voice, whatever I am speaking, my words, my speech is now getting transmitted over the channel. From the phone, it is going through the phone's network to whoever I am speaking to. Once you go past this, then it's the block diagram is sort of the same. There is a decoder in this case, and where I am transmitting I have to encode. So there is an encoder here, and then this is followed by now we will say that the DSP sort of has both the output path blocks and input path blocks, and then there is the driver circuitry that will drive the headphone, and then I have the microphone circuitry which connects to the microphone. So this will connect to, this is let us say headphone left, this is headphone right, and this will connect to maybe mic and possibly a mic ground as well, right. And there is a headphone ground as well that I haven't, maybe I will add it here. So now if I am let us say looking to make or receive a phone call, these are all the blocks that come into play. Again you can see that there is a RF / connectivity block, and then we have a audio block. Now, if I go back here for a second, same way I can say that I have an RF or a connectivity block. Maybe RF or connectivity is an incorrect way to say it. So, we have a connectivity block. So, let me just remove the word RF from this place. So, I have a connectivity block and I have a audio block, right. So, now, so in both cases we have here also, let me just going to remove. So, in both cases we have the connectivity block and the audio block. So, what we can do now is try to sort of say, okay, let me list all the subsystems which will go into making a product like this. So, we found two subsystems, right. We were able to see that when you listen to music or when you make or when you are speaking over the phone to somebody else, at a minimum you have to have a connectivity block or a connectivity subsystem, you have to have an audio subsystem. That is the minimum thing you need. So, let us say list of subsystems. So, first one is the connectivity subsystem. The second one is the audio subsystem. What are the other subsystems that have to be there? Now, these are all active circuits. Active circuits require power. So, you need to provide some supply from the battery. So, you do not just connect the battery and be done. So, let us say it is a portable device that you can recharge and use. The battery now is connected to your system, but you need to provide supplies that these different subsystems can work with. And the interface between the battery and these blocks is usually done by something called a power management subsystem. So, what a power management subsystem does is work off the battery and generate different supply voltages that can each be provided to these subsystems. So, for example, the connectivity subsystem might say, okay, I want a 1.1 volt and a 1.8 volt. The audio subsystem, because it has a driver that has to drive a load, might say I need a 1.1 volt and a 3.3 volt. It is the job of the power management subsystem to say, okay, I have a battery which maybe goes from 3 volt to 4.2 volt. I am going to, from that battery, generate very regulated voltages that can be used to power these systems. We look at this in more detail as we go along. It is just good for us to list. So, that is the power management subsystem. Now, like I said, this is a portable device, and again, if you have had a Bluetooth headset, you would have of course charged it, which means that there is a rechargeable battery, maybe a lithium ion, maybe a lithium polymer battery that is in your system, in your device, in your product, and that needs to be charged. That charging happens through a charging subsystem. So, then we have the Is that all, or are we missing something? Right. So, now let's think about it a little bit more. What else happens when you buy a Bluetooth headset? You turn it on, some light comes up, right, so that you know, I actually turned on the device. When you put it in pairing mode, that light does something else. So, again you know, okay, I took some action, I have no screen, nothing for me to know what I am doing. The only way I can get feedback on my action is through a visual alert. So, we have a LED subsystem. So, the job of that LED subsystem is to be able to provide visual alerts or visual cues that tell the user this is the state in which the system currently is. So, if you go critically low in battery, for example, you might have a system which keeps flashing that red light. If you go into pairing mode, it might flash blue and green alternatively, so on and so forth, right. Now, these vary from product to product, of course. But it is interesting to consider, okay, if I have 3 colors and a range of patterns, breathing pattern, a blinking pattern, fast blinking, slow blinking, that allows me to now provide an array of visual cues that make the user experience very kind. That is achieved by the LED subsystem. And then what else, what other subsystem can we think of? Now let's again think a little bit about how products get used, right? If you've had a earbud, an AirPod class product, one of the things you would have experienced is that it detects when you put the device into your ear, right? That it is able to say, oh, okay, now you've plugged in, I should detect that, I should again play a tone, show something that tells you that, yeah, I understand that you plugged in the earbud. That is achieved through in some cases through an IR sensor. You can have a range of different ways in which you can detect it. Sometimes they have a combination of a pressure sensor and an IR sensor. But at a higher level, what it means is that you have a sensor subsystem, and the job of that sensor subsystem is to be able to say, okay, now I have different ways in which I can interact or the user can interact and the device can interact with the environment. So, the user can interact with the device can interact with the environment to be able to offer a user experience that is very seamless. I just gave 2 examples of sensors. It can be a touch sensor, it can be a temperature sensor, it can be an array of different sensors that cater to different types of use cases, right? I mean, now you have rings, you have watches that all come with again an array of these sensors that let you get very, very high quality metrics about your body vitals, right? So, that is achieved through the sensor subsystem. Right? So, again, you think about it, we just started with a simple Bluetooth headset. It's not conceptually, it's not very complex, and even a simple, seemingly simple, and conceptually simple system like a Bluetooth headset has a number of subsystems that have to work together, and at some level it is the responsibility of the embedded system designer to make sure that these subsystems work together seamlessly. Does that now mean that, okay, as an embedded system engineer you should know the in and out of all of these subsystems, or do you say, no, I have a, you imagine that, right? Can I be an expert of a connectivity subsystem? Can I also be an expert of an audio subsystem? Can I understand every block that goes into these subsystems? Is that reasonable to expect that I should know all of that and also know how to put these completely different subsystems together? Where exactly does the embedded designer draw the line? Where does he need expert knowledge? Where does he need working knowledge? These are all interesting questions to ponder over, and that's sort of where we will lead this conversation. Maybe what we will do before that is try to dig little deeper into these subsystems, right? So, we can say, oh, okay, now we are looking at each of these subsystems. We are able to partition that subsystem into digital blocks and analog blocks, and maybe get a sense of, oh, okay, when we say analog systems, these are the kind of subsystems that we are talking about. And now if I have to integrate or if I have to put all of this together to make a product, what are factors I should consider in my decision making? As an end user, what does a customer expect of me, the embedded system designer, in terms of the decisions I make? That's where we will go with this. So, we will start by trying to map out block diagrams for each of these subsystems.